Boyuan, please take it from here.
All right, thank you. Okay, can you see my title slide?
Yes, but not yet in presenter mode.
Great.
Now
okay, hello everyone. I'm Boyuan Liu from UT Austin, and first I'd like to thank the organizer of this virtual conference. It's my pleasure to share with you my recent research for the statistics of population 3 binaries and their implications on early structure formation. This talk is based on some of our recent papers. I think most results will be from this paper, Dynamical Evolution of POP3 stellar systems and the resulting binary statistics. Okay, here is the outline of my talk. Let's get started. So why do we care about binaries? This is also mentioned by previous speakers. Binaries are actually important for understanding the observational signatures and imprints of the first stars. First, with close binary interactions, the stellar evolution can be changed, and this will change how stars look like directly. Second, contamination from the wings of companion stars and different supernova conditions shaped by close binary interactions can change the abundance patterns of extremely metal Perth stars that we can observe today. So this will also affect stellar archaeology. Last but not least, binary stars are also progenitors of X-ray binaries and black hole binaries. X-ray binaries can have very interesting feedback on the formation of the first galaxies and also the thermal evolution of the AGM. For example, can be recorded in the 21 centimeter signal. I think our next speaker will talk more. And also for binary black holes, if they could merge within the Hubble time, they will be important sources of gravitational waves. Actually, some of the events detected by LIGO could be from POP3 stars. So binaries are important. However, it is challenging to study POP3 binaries because we don't have direct observation, and we have to rely on theoretical models. Here, this plot shows the standard picture of POP3 star formation. At the beginning, we have a collapsing cloud. Then a protostellar disk is formed. In this disk, fragmentation and accretion onto protostars will continue until feedback shut them down. I call this phase phase 1. Thereafter, we have a newly born cluster of POP3 stars, and then binaries of stars will also further be formed by n-body dynamics in this cluster. I call this phase 2. As also mentioned by our previous speakers, due to limited computation power, it is impossible to simulate the entire phase 1 with enough resolution to capture the detailed fragmentation process. So currently, the link between phase 1 and phase 2 is still unclear. Therefore, previous studies have adopted simplified treatments for POP3 binaries. In previous studies, there are two main assumptions for POP3 binaries. The first is to assume that POP3 binaries are similar to their present-day counterparts. The second is to take POP3 protostar system from small-scale, high-resolution hydrodynamic simulations and turn them into POP3 clusters directly by boosting the masses of protostars. These two assumptions have one common problem, that is, they tend to overproduce closed binaries. Why? The reason is that, this is also mentioned by our last speaker, binaries of protostars tend to expand during accretion as the system gains angular momentum. So in light of this, we designed a new model to establish the link between phase 1 and phase 2. With this model, we can explore the dynamical evolution of POP3 clusters and also derive the binary statistics. Here is an overview of our approach. First, we generate initial conditions as the end products of phase 1 for such newly born POP3 clusters. Then we run pure n-body simulations for a sample of clusters from which we can derive the binary statistics. So the main advantage of our model is this initial condition model, which is the link between phase 1 and phase 2. So this model has three elements: global properties, inertial mass function, and internal structure. For global properties, we make use of the scale-free nature of POP3 disk evolution. It is shown by self-similar transformation that the radius and mass of the system satisfy very simple parallel scaling relations with time. And also, if we also with self-similar transformation, we can normalize the times in different simulations with different resolution according to the density threshold used to identify protostars or create sync particles. In this way, we can compare different simulations. And it is found by Sousa that the number of surviving fragments also follows a simple parallel. And it turns out that most small-scale simulations are consistent with one universal solution for Pop III disk evolution, shown here. With this universal solution, we can associate the global cluster properties at the end of phase 1 with 2 timescales. First, the fragmentation timescale tells us when the number of fragments is saturated. I'm talking about surviving fragments, not all fragments. And then the accretion timescale tells us the size and mass of the system when accretion is shut down by feedback. Note that this universal solution has captured the feature that the system can expand during accretion. Okay, here is a plot showing that how the universal solution feeds simulation data. Each data point is a set of simulations. And you can see the fit is pretty good. And we have typical scatters within a factor of 2, shown by the thin dashed lines. For the internal structure, we construct the newly born cluster as a hierarchy of binaries based on the properties of hierarchical fragmentation learned from small-scale simulations. The basic idea is that here I show you an example. These dots are stars. Each star is a node in this tree, and each connection between 2 stars tells us the relative locations of these 2 stars in a 60 phase space. And then in this way, we can generate the distributions of stars in this phase space. Okay, now let's look at the results. Let's start with our fiducial model. So in this fiducial model, the initial cluster size is about 0.15 per sec. And the total mass of stars is 400 solar masses. And the typical number of stars is 13. And this plot shows the distributions of 4 binary properties: the primary mass, separation, eccentricity, and mass ratio. And here, our results are denoted by the purple histograms. And we also show literature results with contours. Note that this solid contour is for protostars, not stars. That's why you can see it's like we have larger separations because that's protostars. The biggest difference between our results and those in previous studies is that we significantly underpredict or the fraction of stars in closed binaries with separations smaller than 100 AU. It's like this area. Another interesting findings are we found that the distributions of eccentricity and mass ratio are almost uniform. The results from other simulations with different parameters are similar as long as they follow the universal solution. Next, let's look at how the binary statistics depend on model parameters, especially for those extreme cases in which the universal solution does not hold. It turns out the most important parameter is cluster size. And besides, internal structure and stellar collisions are also important to some degree, but the most important thing is cluster size. So here I have a very busy plot, and it shows how many properties of binaries and clusters depend on the initial cluster size. In these models, I have fixed all the other parameters to the fiducial values, and I only change the initial cluster size. Let's just focus on one quantity on the top right here, and this is the median separation. Here is the zoom in to that panel. Here we have a solid curve and a dashed curve. These 2 curves are from our models. And the solid curve shows the results for all binaries, including the binaries in quadruple and triple systems. And the dashed curve shows the results for isolated binaries only. And literature results are shown with horizontal lines. And on the larger end, you can see actually 3 data points at 1 radius. These are 3 different implementations of the internal structure. And on the lower, smaller end, you can see 2 data points. And for this lower one, we have reduced or surprised stellar collisions. As you can see, the median separation is almost proportional to the initial cluster size when we ignore stellar collisions. Interestingly, we can also reproduce literature results if we set the initial cluster size to exactly what they adopted, shown by these right regions. Finally, I would like to talk about some implications of our results. This plot shows the co-moving density of accreted mass in POP3 black holes. The solid curve here shows the accretion from the ASM derived from cosmological simulation. The long dashed curve here shows an example for accretion in POP3 XB binaries assumed in previous studies, which is pretty high. And all the other curves are the results for XB binaries from our models. And you can see, and also this shaded region is the amount of accretion needed to explain the observed X-ray background. So, of course, the biggest finding is that we predict that the accretion of X-ray binaries is actually pretty low. It's much lower than assumed in previous studies by about 4 orders of magnitude. And also, this accretion in X-ray binaries is actually overwhelmed by accretion in, from ASM, except for very early times, above, say, redshift 12. So the reason is that in our simulations, the efficiency of forming X-ray binaries are actually very low. We can form one X-ray binary in only every 10 to 100,000 solar masses. And also, most of our X-ray binaries, they are only active at the gent phase of the donor star with very short lifetimes and little accretion. In summary, we found that binary statistics are highly sensitive to the initial cluster size. If we set the cluster size to what is expected from the universal solution, our models predict that the fractions of stars in closed binaries are actually much fewer than assumed in previous studies. As a result, we also have very low efficiency of forming X-ray binaries. Therefore, we conclude that the feedback from POP3 X-ray binaries is likely unimportant for the global evolution of the AGM, although they could be important if locally if they are formed. At last, I would like to share my outlook to future studies. First, to go deeper, we need to establish the link between phase 1 and phase 2 with more advanced simulations. We need to run the simulations longer with higher resolution. And to go broader, we need systematic investigations for the environments of POP3 star formation, such that we can evaluate how the outliers of the universal solution contribute to the overall properties of POP3 binaries. Last, finally, as our models show that closed binaries are probably rare in protostar in POP3 stars, then it's important to consider ex situ channels for the formation and evolution of POP3 black hole binaries, such as dynamical capture of black holes and also three-body interactions with surrounding low-mass stars in dense star clusters. For example, our binary statistics have been applied to explain one recent reported merger event detected by LEGO. This event is GW190521. This event is really interesting because it has two black holes in the classical mass gap of positional parents to the supernova. So it is really difficult to explain this event with classical binary evolution models for POP1 and POP2 stars. But POP3 stars are interesting or promising progenitors for such black holes. This plot shows the merger rate densities of such events similar to this event from many different models based on our binary statistics. Considering isolated evolution and also environmental effects. And you can see these models have good agreement with the observed rate, which is shown by the shaded region. I think that's the end of my talk. Okay, thanks for your attention and feel free to ask me questions.
Thank you, Boyuan. That was a very nice talk. We have questions on the Slack. So, for example, Stefan is asking, for the initial conditions of the n-body simulations, how do you distribute the stars in phase space, and how long do you run the simulations for?
Okay, that's a good question. So we have learned from small-scale simulations that fragments are formed around persisting fragments instead of all around the central massive fragment. So that's why we construct this as a hierarchy of binaries. It's like each star is connected with another star as like in the form of a binary or pair. And then we generate binary properties or parameters for these pairs. And then once, say, we know the separation and we know the masses of two stars, then we can generate the velocities. And also we assume that they are all distributed in a disk with some scatters, vertical scatters. Yeah, that's the basic idea. Is every star is connected with another star. That's how we generate the initial condition for the distribution in a 6D phase space.
Awesome. You just answered one of the other questions as well. And as a last question, can you explain why you don't find a compact, smaller than 1 astronomical unit binaries?
Well,
why do you have this gap?
I think it's just because of the cluster size. We in our case, the initial size of the cluster is much bigger than assumed in previous studies, and also this also depends on how we implement internal structure, and we have shown that if we have implementation that is biased towards closed binaries, we can enhance the fraction of stars in closed binaries, but not much. It's still difficult to form closed binaries, especially for massive stars, because they will, to be massive, they need much accretion, and during accretion, they will expand if we cannot efficiently transport angular momentum away. But these are all based on the universal solution. It's possible that in some cases, or maybe in most cases, the universal solution doesn't hold, because this is learned from our simulations and not constrained by observation. And it's possible that, say, we have some mechanism to transport angular momentum away, and in reality, the cluster is smaller, then we can have more closed binaries. But we still don't know now.
Okay, thank you so much, Boyuan.